Okay, so this next slide already shows us a picture of carbon, the element, which has 4 valence electrons because it's in group 14. So I guess its structure would be 2s2, 2p2. So that's 2 plus 2 equals 4. Okay, so here's our Lewis structure. So the question is, how many bonds do you think carbon is going to make? How many connections would it want to make with another molecule, with another atom maybe? Maybe we've got a bunch of atoms hanging around and they're going to connect. So I want you to go into Top Hat and answer that question now. Also, be sure to explain your logic. So don't just tell me why or how many bonds, but rather also tell me why you believe that. Okay, so let's look at the reminding ourselves how we can find valence electrons. Okay, so hydrogen's in group 1, so it's got, and it actually is the smallest, oops, it's actually the smallest element, so of course it must have just 1 valence electron. Okay, and then we go across to the next one. Let's see, this is going to be okay. Helium is 1s1, 1s2, so that's going to have 2 electrons on it. Lithium goes back down to group 1, so that actually has just 1 valence electrons. The 1s1 and 1s2 electrons are what we call core electrons, so they're like stuck in there. Okay, Be is in the second group, so I'm going to put 2 electrons. And then we jump across to B in element number 5, boron, and that one has 3 electrons, so I'm just going to put 3. Carbon is in group 14, so it's got 4 electrons. Nitrogen is in 15, so it's got 5 electrons. This is a little easier to do on paper than it is on an iPad, but you'll get the right idea. And then oxygen is right next to nitrogen, so let's do 1, 2, 3, 4, 5, 6. Oh, there's actually 2 electrons on that side there. Fluorine is even farther to the right. It's in group 17, so it kind of follows that pattern of adding 1 more electron as we go across the periodic table, so 7 in that one. And then finally we get to neon. Okay, so neon is all the way to the right-hand side, so that means I'm going to have a full 8 electrons in the outer shell of neon. Okay. There we go. So as you might imagine, the pattern kind of continues. So like here we have sodium that has 1 electron. Magnesium is 2 because it's in group 2. Aluminum is 3 because it's in group 3, and on like that. Okay, so you can finish filling in this table. But it's a reminder that the group number actually tells us the size, or rather it tells us how many valence electrons there are for, at least if you're just counting the main group elements, which are groups 1, 2, 13, 14, 15, 16, 17, and 18 on the periodic table that I gave you. Okay. So the thing about Lewis structures is that they show us, they give us a visual representation of where the electrons are at, which also helps us to figure out some important properties of the molecule. Knowing what kind of bonds something has gives us a little bit of information about the kind of energy it has. More bonds, more energy. It also tells us something about where the electrons are, so that tells us where the bonds are. And that helps us to predict how a molecule is going to react. Okay, so remember this word bond means the attraction between 2 atoms, and that's because the 2 electrons really want to be paired up. They want to have one pointing up, one pointing down when they bond in the middle. So you can imagine a carbon-hydrogen bond there is really kind of these two electrons that are buddies, and they're balancing each other out really well. So that's very stable. Bonds are always made out of electrons, and a single bond is 2 electrons. A double bond is 4 electrons, because you're doubling that, and a triple bond is 6 electrons. Those are all called, those double, triple, single bonds are all covalent bonds. So we have another kind of bond that can occur, though. It's called an ionic bond. They still want to occur because they're trying to become stable. That is to say that they're trying to get 8 electrons. In the case of ionic bonds, they achieve stability by transferring electrons from one into the other. They don't share the electrons the way that covalent bonds do. So we have some terminology to know. The word cation comes from physics, and it means something with a positive charge. So that means it's an atom where you have lost electrons, leaving more protons behind. And I remember that cations are positive using this phrase. Cations are positive, like a cat's paw. I know, it's hilarious. Try to contain your enthusiasm. But cations are positive is one way to remember it. Another way that you can maybe remember this is also because the word cation itself has a plus sign in it, so positive. So however that works best for you. The other phrase that we sometimes use to describe things that are charged is anion. Anion means a negatively charged particle. It's important to notice that metals tend to become cations and nonmetals tend to become anions. But when you combine the two together, you make an ionic compound. Those generally exist as what we call crystalline structures. So let's take a look at what a crystal looks like. If you get out a piece of salt and you get a magnifying glass and you look at it, that salt is always shaped just like a cube. Always. Just like that. The reason for that is that on a molecular level, sodium and chlorine connect with each other because sodium is a positive ion and chlorine is a negative ion. They want to be around each other, and they happen to arrange themselves in such a way that it makes a cube. And so the shape of the molecule on the microscopic, the atomic level, impacts directly the macroscopic thing. If you don't believe me, pause the video and go look at a piece of salt. Okay, so now you believe me, right? Good. So we can draw the diagram that most closely represents the way salt atoms are actually stacked together, and this is called a crystal structure. So this top structure right here is one representation of a crystal structure. What this doesn't show us, though, is the ionic bond that occurs between the metal sodium and the non-metal chlorine. So in order to do that, we can draw little sticks between them, like this.